So in this problem, we're told that a stick of length L and uniform mass density is attached to a frictionless hinge on the floor. You nudge it just slightly so that it has a negligible velocity, but it will then lose balance and fall down. And we're asked how fast this top point is moving by the time it hits the ground. So this is going to be an energy conservation problem. We have a before and an after. In the before phase, we know that the center of mass is exactly halfway up the stick. And so we know that energy initial is going to be just mgh is equal to mgl over 2. Since energy is going to be conserved, energy final is going to be the same thing, but it's going to be entirely in rotational kinetic energy, since the block will be vertical, and so no point of it will be above our 0 for ground at the level of the floor. So the energy final is going to be 1 over 2 I omega squared. It's a stick, a long stick, rotating about its endpoint, so its I is going to be 1 over 3 ml squared. So that's 1 over 6 ml squared omega squared. So now we can set the two of these equal to each other. We get that 1 over 6 ml squared omega squared equals mgl over 2. We can isolate omega, which is what we're looking for. Omega squared is equal to 3g over L. Yes, and then omega is equal to the square root of 3g over L. Now that's not quite the endpoint because we want to know how fast this endpoint is moving. So that's going to be a linear velocity. And we know that the linear velocity of any point on something that is rotating is just the radius r times that angular velocity. So then the velocity v of that endpoint is going to be L times omega, which is going to be the square root of 3gl. And so that's going to be our final answer for the velocity of the endpoint on that stick.